All right, welcome to Effective C++ WinRT. My name is Brent Rector. This is Kenny Kerr. We're going to be telling you all about this new language projection for the Windows runtime, the standard C++ Windows language projection. So diving into it. Basically, we're going to do two levels. I'm going to give you a high-level overview of the tooling, what C++ for the Windows runtime called CPP WinRT can do for you, how it will help you, makes development a lot easier and a lot more efficient. And then once got sort of an overall viewpoint of the whole process workflow, Kenny is going to come up and dive deep and show you some of the internals, show you how to be most efficient and what the C++ language projection can do for you. So we're going to have a high-level talk, and then we'll dive deep and answer all your questions at the end. So let's start off with what is the Windows runtime. Now, I'm on the Windows runtime team, been on it for about 9 years now. Historically, we had the Win32 API, flat C-style API. Was great if you're writing C or C++ code, but it wasn't very accessible to other languages. And it's also a flat API. I know back in the Windows 1 days, which dates me, the documentation of the APIs were like 300 APIs. And I knew the A's and B's and C's really well. I didn't know the ones at the end of the alphabet nearly as well, because I could just read through it. Oh, there's the one I want. ANSI to Unicode. Well, we didn't have Unicode. Never mind. So it was way back. Nowadays, I try to come up with an estimate of what kind of Windows API surface we have. And it's a rough estimate. It's like 600,000 to 1.2 million. We have a lot of APIs. It depends on how you count. That's kind of unapproachable. So we came up with the Windows runtime as a language agnostic API for the operating system. It's also hierarchical. So we have namespaces, we have classes. It's a classy programming model, not a flat C-style programming model. And the nice thing about the Windows runtime is it comes with metadata for all of the APIs. So we talked about it's object-oriented. The metadata is really very powerful. It's what actually gives us the ability to produce all the various language projections. So you can actually write programs in JavaScript or C# or C++ or Objective-C or other languages, all targeting the Windows runtime APIs. So this is the modern programming surface for the Windows OS. We still have Win32 and everything that you know and like to varying degrees, but we have this great Windows runtime API. So these language projections, sort of the key phrase that we toss around internally is we want programming in your favorite language to write Windows applications to be natural and familiar. So if there's an idiom that your favorite language uses, we want you to be able to use the Windows Runtime OS APIs using those idioms. And what is natural and familiar in one language may not be natural and familiar in another language. But with this metadata about the APIs and the Windows runtime that lets basically any programming language access them, we can expose those APIs in a natural, familiar way to you. Now, C++ for the Windows runtime, or CPP WinRT, because I can say that much more quickly, is a language projection. We have another one, which I'll show you briefly, called C++ CX. That was an earlier projection for the C++ folks. And we'll compare the two briefly and show you why we think this is an improvement. So what is CPP WinRT? As I said, it's a language projection for Windows runtime APIs. At its bottommost layer, really, it's a header file-based library, a C++ header file library, like STL or Boost. It also comes along with a tool that you can point it at a metadata file that describes a Windows runtime API, and we will generate the library for that API. So regardless of the language that somebody implemented a Windows runtime control library or utility library or whatever, you can get C++ header file wrappers over those and access those APIs naturally. So how do you get CPP WinRT? Well, Visual Studio 2010 15.7 released today. You download it, and this header file library comes with Visual Studio. It's actually been in all the RS4 beta previews up till now as well, so you might have actually already tried it. What can you do with it? Well, basically, every OS API, or really any Windows runtime API, whether it's an OS API or some third party, to you is just a C++ class. You just instantiate it and you call members on it just like you would any other C++ class. We go to great lengths to make it look, feel, and behave just as it were any other C++ library. And you'll see when Kenny does the deep dive, we go to great lengths to say, you don't have to learn a new type system. You don't really need to know the Windows runtime type system. You can just use std strings and std vectors and pass them into our APIs, and it just works. And we make sure and do that in a very, very efficient way. Now, for most people, they're going to just use our library to call APIs, to use them. But if you want to implement Windows Runtime API, the nice thing about implementing something as a Windows Runtime class library is it's accessible now to anybody using any language. So a lot of people think, well, how about implementing it? Well, you can implement it in standard C++ as well, too. So the nice thing, and I kind of glossed by it, so I want to come back, is this is all standard C++. If you've ever seen C++ CX, we had non-standard data types, non-standard keywords, hat pointers, ref classes, all this stuff that hurt my eyes to look at, especially the little pointy hat things. So here, everything I'm going to talk about today is just standard C++. We actually test with the Clang compiler, the Microsoft compiler, to make sure we're just standard. Now, that said, we're very, very modern standard C++. We're C++ 17. And we have features that we're talking to the standardization committee in C++ 20 that we'll leverage if they get adopted. So we're actually using very, very modern standard C++. So you need a really new compiler. We break the compilers all the time and then get them fixed and then use the features. Now we're also finally going to show you a preview of our XAML support. So a lot of people that want to build UWP applications, they want to use XAML for their UI framework. Well, we've taught the XAML compiler to generate code behind files in our language projection. Previously it did C++, CX, or it did C#. Now it does CPP WinRT as well. Now this is a preview. You may find some bugs. The tooling is lagging a little bit behind where I wish it was, because I wish it was done yesterday, like every other project. But we're going to flesh it out. We want your feedback. And I'll show you a completely working photo editor app written in nothing but standard C++ using XAML. So let's look at each of these three stages at a very high level before we get to Kenny's part where he'll deep dive. Let's say you want to write this code. I want to fetch a web page and display it somehow. This is really what I want to write. I have a URI that references the resource on the web that I want to talk to. I have an HTTP client object that knows how to talk HTTP to get it. I have a method that will go and fetch it for me. Now it happens to be an async method, and now I have to think about, do I have to spin up a thread, and how do I wait, and do I blocking wait? Well, no, let's just put a .get on the end here and make it synchronous. This is what I would like to write. But let me show you what internally at Windows we've been writing for the last 8 years. That very first line translates to all this code. And I have helper functions and macros here to simplify it. This is just creating a URI object, constructing it with a string parameter. The next line, the HTTP client object, is an equivalent page of code. And then the third line, calling the async object, waiting on a thread to finish, doing all that's probably 5 or 6 more pages of code. This is what, up until now, we've been writing internally at Windows when we want to do Windows runtime. We've not been evangelizing this. I don't think it would have gone over too well if we had. This is WRL, the Windows Runtime Library. But we realized that that was sort of a productivity barrier to writing in C++ to the Windows Runtime APIs, so we created C++ CX. This was a number of years ago when the Windows Runtime itself was new, so we basically modeled very closely some concepts in the Windows Runtime. We have these hat pointers. These are reference counted objects. So they're smart pointers really, but they know how to add ref and release. So we have ref new. Well, you have to allocate. It's not really new. I'm not just heap allocating an object. I'm going into the Windows runtime and row activate instances, the low-level API. But I'm basically activating a class. And I need to tell CPP or CX, that's what I want to do. So I have ref new. I have these hat pointers. If I want to do async work in C++ CX, generally the way most people use it is with the Parallel Patterns Library, PPL. And PPL, you can create a task, you can give it a lambda, there's the return statement is the lambda, it spins up a thread or grabs one from the thread pool and runs the lambda on it. It has the thread pool thread signal an event when you're done. The main thread's blocking on the event because of the .get at the end. I just really wanted to get a web page. That's all I wanted to do. And I'm now using non-standard data types as well. I got this web page. I thought I got a string, but what the heck is this data function that I'm calling? I need a char star to pass to printf, because that's what printf deals in. So it turns out there's a non-standard property, or technically a method, on the platform string hat that I got back from the function call. And then I go and I throw some more stuff around. Even main has some types that I've never heard of before. It's like, I never actually wrote much. I protested every time I had to, much CX code, just because I'm an old-fashioned C developer and C++ developer, and I didn't like this dialect. And so we came up with this idea, let's make a standard language projection, one that's just pure standard C++. It can work across multiple compilers. Now, it was a challenge. We've been working on it for 2.5 years or so. But I want to compare where we're at now with where we came from with CX. This application is not bad. It's about 80K bytes. But, of course, it has all this weird data types that I don't understand. Let's go back to the code you really wanted to write. URI, get a client, fetch the page synchronously. Well, I include header files that are shipped as part of the Windows SDK. They're all in this WinRT folder. It turns out there's a Windows Foundation.h that are the ABI COM interface header files. And I wanted ours to be called Windows Foundation.h. That's the good name, because those are the types that are in the Windows Foundation namespace. So we put them in a subfolder called WinRT. You'll find about 220 namespace header files in there. I need the Windows Web HTTP client class, so I include that. I don't like typing all that, so I have a using namespace. I'm using printf, so I include std.io. Note, when I get my page class back now, it acts like it were a standard C++ string type. I can call cstr on it to get the char pointer that I need to pass to printf. And when I wrap the thing with the regular main, it's the regular main that you know and like considerably. There's one call that you have to make to make the Windows runtime initialize. CX did this for you because it knew you're using all these weird main entry points. It knew, oh, he wants to use the Windows runtime. Well, we have a C class that does that for you in the department. And of course, the destructor will uninitialize at the end. And that's it. That is your standard C++ program. Bonus, when you compile it, we're 23K bytes instead of 80. So in this case, we're 70%, it's only 70% smaller than the CX version. Now, to be fair, the majority of that's because I don't use PPL. The parallel patterns library, it's template-based classes. They produce a lot of overhead when you instantiate all the templates. A more typical result we've seen again and again and again. If you take a standard CX app and you change it to C++ WinRT, it has some PPL because it uses some async functions. You get about a 30% reduction in size. Conversely, I have taken another app that was all network communications, all async operations, all PPL, like every other line it seems like. I got the same 70% that you see here. So we're more efficient, we're standard C++. 2 wins. Doesn't taste good or smell great, but you know, what can I do? Everything I've shown you now, you could do today with just our header files. All I did was include some header files and instantiate the classes. Let me go back and look at the classes. Notice the URI variable there of type URI, Windows Foundation URI. I just allocate it on the stack, and then I call methods on it with a dot. Come back to this later, but we basically say, use our classes as if they were the object itself. It's not really, you'll see shortly, but as if it were the object itself and call methods on it. Everything here is just in a header file library. There's no runtime that you need. Just include our headers and compile. However, we didn't think that was good enough. We wanted to help you build great applications in a more efficient way, so we wrote a Visual Studio extension. Eventually this will ship as part of VS itself, but because of timing and we want to rev it because it's new and we have the XAML-based preview content, it's up on the Visual Studio Marketplace. You'll get a pointer to that in a second. You get a vastly improved debugging experience once you install this extension. I'll show you that shortly. We also have new project and add new item templates. So if you want to build a brand new CPP WinRT based application, we have templates to get you started. It's not that hard. Well, it's not that hard for those of us who have dealt with it every day to get started manually, but these templates make it really easy. And then all the XAML application integrations so that when you build an application that is XAML, we do the right build steps to have it produce the right code behind files in the right C++ dialect. So how do you get this? 2 ways. You can go to marketplace.visualstudio.com and search for CPP WinRT and then install it. Alternatively, if you're running Visual Studio 2017, you go to Tools, Extensions, and Updates, search for the same thing. We found, it's kind of weird, we published this Friday, and I was going to keep it quiet, and we've had about 100 downloads a day since Friday. We haven't even written a blog post. This is the first public disclosure of our physics. And people found it somehow, I don't know. We've already been getting critiques and reviews ranging from we found this bug to this is fantastic, this is great. I like both. I kind of like the great a little bit better in one way, and I like the bug reports better in another way because it helps us make it better. But once you install this physics, let me show you what it will do for you. Now, first, I need to define a term. All the types, well, all's too strong. Most of the types that you include these header files and use, like the URI type, the HTTP client type, are what we call projected types. They're not really the URI class. That's built into the operating system. when I instantiate that URI object on the stack, it's really just a really smart pointer to the thing in the OS. As such, it really only has one piece of state, a pointer to the real object. And Visual Studio very kindly shows you exactly what it is. So, wow, it's got a field called m_PTR, and it points to an I_unknown vtable. And there are its addresses, as if you really wanted to know that. Well, I didn't find that as helpful as maybe you do. And by the way, you get the same thing in CX, so we're not lagging there, or in raw C++ with the WRL code that you saw. But once you install our extension, it knows that this is a projected type. It's really just a smart pointer to something behind. And remember that metadata? I have metadata about all the types. So my debugging extension now can show the URI object like this. I see all of its properties. I see its values. I'm really just looking at this instance of a smart pointer, and what the extension does is it goes and looks at the metadata, sees what properties are available, synthesizes a call to the prop get functions to get the value, and then formats them accordingly. So I think this is a win just for the physics alone. If it did nothing else, this was one of our key features that people loved. So let me switch over to my demo machine real quickly, and I just want to show you some of the templates. And show this to you live. Basically, when you say File, New Project, and you go to Windows Universal, these things down here at the bottom with the blue icons, these are the project templates, 3 of the 4 that we have right now. A blank app, that's an empty XAML application with just a blank main page. Actually, it has 1 button on it. We have the core app. This lets you write DirectX or game-like apps. And then we have the console application. Oh, and we also, which is not in the UWP, so it's over in Windows Desktop. And then we have runtime component, which lets you implement a Windows runtime type. I'll talk about all of these to varying degrees, but first I wanted to go to the console app, walk you through the structure. This is the app that you saw before. One key thing, which I have to mention, is the PCH file. Now, we have a tool that reads the metadata and generates these classes. It's a compiler called cpp_winrt.exe. It's in the SDK. It runs as part of the build process for some other usages. But the system headers, which were generated by that as well, there are about 40 megabytes of header. That's why we have them in separate namespace headers, so you don't have to pull in the whole 40 megabyte each time. For a little app like this, pulling in these couple of headers, which they'll pull in their dependencies, probably results in maybe a 2 to 5 second increase in your build time. But if you're building a big XAML application, like one I'll show you later, you pull in dozens of these headers, and they pull in their dependencies. It can add about 30 seconds to your build time. That's the worst I've seen. So I don't want to do that every time. I do that in the PCH. I take that hit once, and then my incremental dev time is very fast. In fact, the last few times I've tested it, incremental builds are faster than they were in CX. You pay a big one-time cost in the PCH, but put all your includes there. And let's start this thing up. Okay, we took the breakpoint. We look at the URI. There's my debugging that you saw before. We hit F5 to go to the next one. And I have an exception. Oh, because I have no internet connectivity on this box. And I'm not going to take time to do that, but I was going to show you the page. If you looked at the page type, You could find out that we also have the debugger extension on that. I can browse over it. I could see all the text. I could invoke the visualizers. Since that's an HTML page, I could click on the HTML visualizer. You get all the debugging that you had before, plus some, as you can see here. All right, back to the slides. All right, so we've talked about using system Windows runtime types like HTTP client or URI. What about ones that you get from third parties? Maybe you get a Telerik control, or maybe you get a class library, a WinRT class library from some third party, like the Win2D library that lets you do retain mode graphics nice and efficiently. Well, we support that too. Basically, once you add a reference to a metadata file, which is a WinMD file, the build system installed by our Visix recognizes that your project has a reference to a WinMD file, runs our compiler to produce the header file library for the types in that WinMD file. In fact, technically, that's all we did when we generated the ones in the SDK. We just ran it on the WinMDs in the header. Kenny will talk about that more. So here's an example. Win2D is a Windows Runtime API library that's available via NuGet. So I can go to Visual Studio and download managed NuGet packages, search for Win2D, and install this thing. And what happens? In my project, I get a set of WinRT header files. They're located in a similar structure to the system ones under that WinRT directory, one for every namespace in that library. And now how do I use them? I use them the same as any other C++ class. I include my header file, because we like long names in the Windows runtime. I put a using namespace so I don't have to write so much. And then CP effect, I just declare an instance of it. And then I call methods on it. It's just a C++ class, really. I mean, this is how easy it is to use Windows runtime types. So high level, add a reference to a WinMD, and you get a C++ WinRT projection of the types in that WinMD, just automatically generated for you. So that's the two aspects of consuming Windows runtime types that somebody else has written. What about writing your own? Well, the problem up till now, when you're writing a Windows runtime type, is there are class factories involved, there are class instances, there's query interfaces, a lot of COM level, low level goo that you have to manage. Not with us, not with our language projection. The workflow here is a little different. This is where we probably need to slow down and spend a little time. If you tell us what the Windows runtime class should look like, and we do that by writing IDL, but not your father's IDL, not my IDL, brand new IDL, IDL 3.0. We didn't even want to call it 2.0. It's IDL 3.0, which is going to look very similar to something you might have seen. Once you write this class description, we generate everything for you except the actual implementation of the functions. So if you say this class has 2 properties, a method, and 3 events, you will have to generate the body. Well, you have to provide the implementation of the bodies of those methods. All the boilerplate we do for you. So we will actually generate header, basically source files. We'll generate in a hidden folder. Let me slow down again. Let's go back and look at the IDL. I write the IDL, we give you the implementation of the classes. It's all implemented with throw, not implemented. And you fill out the body. And then you go, oh, I forgot a property. I need to add 2 methods. You go to your IDL, you add them again. We don't want to overwrite all your work. We're really paranoid about that. So we actually generate this skeletal file often in a sort of a tucked away directory. It's in the generated files sources folders. So you can go there and you can copy and paste. I'm going to show you this. I just want to give you a high level. So we'll never overwrite your implementation. And then we have base class. We have a base class in the class name.g.h that does all the Windows runtime goo. Class factory stuff, interfaces, putting the right interfaces, methods on the right interfaces, etc. All you implement are just a standard C++ class. So this is Microsoft IDL 3.0. It has like one of everything in it, just so I show you, no matter what you want to do, it's not complicated. This is more complicated than most that you will write. But I have a delegate because I want to define my own event. This is a photo object, and let's say I have some AI that can do photo recognition on it and fire an event when it recognizes. It would be like the Scott recognizer if you saw the keynote this morning. So I have a delegate that describes the signature of the handler. And then I have this class photo. I'm going to use it in my XAML application later, although a slightly different version. And I want it to find file property changed events. So there happens to be an interface that XAML uses for property change notifications. So notice :photo, Windows UI XAML data, I notify property change. That's all I have to say is this class needs to implement that interface. You, by the way, will not write a line of code to implement that interface. It's all done in the base class for you. I want a couple of constructors. I have a read-only property. That's the one with just a getter. I have a read-write property. I could have wrote brackets get : set : but I don't like writing extra characters, so I just say, oh, by default properties are read-write. I have an async method. Technically, that's only a method. Methods are only async based upon the return type. If they return a future, if you will, a future-like type, then they're async. But that's just a method, really. And then I have an event. Now notice I have concepts in here that C++, standard C++ doesn't really have. Standard C++ doesn't know what an event is. You can write a pattern that does eventing. C++ doesn't really know about properties, read-write or read-only. They know methods that can return values, but how do I know that's a property per se? And then I have interfaces. So this is really the Windows runtime description of the type. Now you could think about it quite a while and go, well, I think this would map to this in my implementation. Well, we do that really for you. When you add an IDL file to your project, similar to like when you added a WinMD, we ran our compiler and generated headers for you. When you add an IDL file to your project, we run our compiler and generate an implementation for you, at least a skeletal implementation. So this is the skeletal implementation H file for that Windows runtime type description I wrote in IDL 3.0. And it's very similar, except it's in the implementation namespace. Notice struct photo, struct because everything's public, so we didn't want to write class and public. We could get away with just one line. Struct public, struct photo derives from photo T of photo. This is the CRTP, the curiously recurring template pattern, where you pass in the type of the class that you're deriving. The base class is being derived from. And then we have the constructor, the default constructor, the one I said. I have the image name property. If you recall, that was read-only. So the property maps to a method that takes no arguments that returns the property's value. We have the sepia intensity property. That was read-write. Notice we have a pair of overloaded methods here. The getter, like before, has no arguments and returns the value. The setter is a void method that takes the new value to be set. My method is just a method, nothing new about that. And then an event, turns out an event really needs two methods. It needs a register for the event and an unregister method. And they're a little trickier, but we generate those for you. So we also, this is really the .h file that we generate for you. There's a .cpp file that has all of these implementations, but I'm not showing them to you because they're all one line. Throw, not implemented. So this comes back to something I brought up before. When you're using a Windows runtime type, it's just that smart pointer, M_PTR. The thing that implements the Windows runtime type can be written in any language. Now, CPP WinRT is a great language to write that in. You can use C#, you can use other languages as well. So I'll point this out maybe in the photo editor if we have time. There are two different classes involved here. WinRT Photo Editor Photo, that's my projected type. It's really the smart pointer. Consumers are going to use that. In my implementation code base, I have the implementation type. And the only real difference in the name is the namespace has the extra node of implementation in it. The reason I bring that up is when we look at an implementation, like a complete application, like the photo editor app, in some parts of the code, I'm implementing the photo type. And other parts of the code, like the XAML pages, I'm consuming that photo type that I implemented. And I'm using two classes that are basically called photo, but they're in different namespaces. It's just good to be aware of that. It comes up rarely. Also, let's say I have 5 classes that I'm implementing in my class library. I would write IDL files. I would get 5 WinMD files. And then when I publish my library, what do I give to consumers? I give them a WinMD and a DLL. I have to give them the metadata about the classes. I have to give them the implementation. So we help you with that as well. We automatically merge all the IDL generated WinMDs into one for your project. And that way you just ship 2 components. And we add, with our visits, project-to-project references work. So if you have one project that implements this class library, you can add a project reference to it and then consume it. Because remember, when you add a project reference to this thing, you'll be effectively adding the WinMD to your project. That causes us in the client code to generate the header files, and now you can consume it just like it were a C++ class. All right, now let's talk about the last thing before we dive deep. Creating applications using standard C++, specifically XAML applications. Now, you've already seen the workflow. When you're writing an application, you're defining types. You're creating a main page type, you're creating a detail page type, maybe you're data binding to a data model type. You're implementing classes, and we've seen how to do that. The only difference is you have a XAML page in addition to the IDL page. The IDL file defines the public surface of the page that the XAML needs to do its code gen. And then the XAML page is the UI that it does the code gen for. So everything's the same here, except now you get one extra file. The XAML page is compiled to yet another base class. Now, I don't know how much you studied CX and how it works. XAML applications using CX used a thing called partial classes. So you wrote one partial class, XAML generated a code behind partial class, and the compiler merged them into the real final class. There is no such thing as a partial class in standard C++. So what happens here is you have your implementation, which is going to look just the same as we saw for photo, and there will be 2 base classes, the XAML base class and the one that does all the boilerplate WinRT stuff. But again, most of the time you don't care. We actually generate these files off in a directory that you don't usually look at most of the time. It just works. You're just going to worry about, here's my functionality, I need to implement these 7 methods or whatever. Okay, so let's say I have a XAML main page.xaml. I'm implementing it. Notice this looks very much like what we saw before. I have struct main page. It derives from the base class template file. The base classes do all the XAML work, all the WinRT stuff. All I implement is the constructor and, in this case, the event register and unregister. I didn't have to do any XAML-related stuff, any Windows runtime-related stuff, or whatever. Everything's done in the base class except the functionality I need to write to customize this type for my particular desired behavior. So with that, what I'd like to do is show you an app that basically, I'll walk you through at a high level, not every line of code, but at a very high level, what the app has done. My machine went to sleep. Okay, so here is the photo editor app, and I'll show you a little bit of the functionality before we look through the code. But this is a XAML app. I can click on a picture. It shows it natural size. I can tell it to fit the screen. I can click on the edit button and select an effects. Now, these effects come from that Win2D NuGet package that I talked about. So I just added a reference to that, and I'll show it to you. But we can do the, how about the sepia? We've been talking about that. So we'll do the sepia effect. Let's see, sepia, apply it. I can change, remove all the effects. I could actually do 2 or 3 effects at once. Anyway, this is basically the, remove all the effects. This is the application. So it does all the natural things at a nice UI. And I will point out now, I come back to it later, we will show you, we are actually going to open source, have open source. That's not what I wanted. I want this. We're going to open source this. It should have been live today, but there was a glitch. There's a URL in the last slide that will show you how to download all this code. There's not a single line of non-standard C++ here. First off, I mentioned it uses the NuGet package. So if I go to Project Manage NuGet Packages, you will see that I have the Win2D NuGet package installed here. I added it to the app. It went and added this WinMD Microsoft Graphics Canvas to the project. Now, when I built that app the first time, let's go show all files. Let's show you the stuff behind the curtain. All of these generated files are generated for you. So there are a lot of them here because I have basically 3 classes. I have the main page, I have a detail page, and I have a photo data model class. And then I have the XAML code behinds, and I have the WinRT code behinds. All this is generated for you. And then if we look up under WinRT, here are all the header files from the graphics, the Win2D package that I generated. That lets me consume the WinRT type, the Win2D types as if they were Windows runtime types using natural C++. They are Windows runtime types. So we'll go to pch.h. I use a number of header files. Remember I said put those all here because this takes about 15 seconds on my laptop to compile. Let's do that once. You don't want to wait that every time. And then it sub-second compiles usually on most changes after that. We'll go to mainpage.idl. This is the main page. This is what XAML needed to know about my main page. XAML has to construct it. You're going to use it in markup, and when you declare it in markup, XAML constructs it, so I need a constructor. I have a read-only property called photos. XAML wants to data bind to that collection. That's where it displays all those photos that you saw on the page. And then when you do a click the back button, I didn't call that out, it does an animation. So I have a method here. It's actually an async method. You can tell that from the return type, iAsync action, that does the animation when you hit the back button. And the reason why I need those, if we go to the XAML page itself, there's photoeditor.main page, so that's the name of the class that it's expecting. That's what I declared in my IDL file. Here's data binding to that method, start connected animation for back navigation. XAML referenced it here in a data binding expression. That's why I declared it in my IDL. If we actually then look at the actual main page.h, well, it's got a lot more stuff on it because it has to represent all of those photos and everything it needs to do and use compositors to display them in the grid. But that's just implementation details for your code. You didn't really need to write all that in the IDL file because XAML didn't care about it. Detail page is the same, not really much to go in there, although I do want to show you one last thing. Let's look for save, button on click. This is my new favorite method in this example. It does 6 asynchronous operations in a row. So first we show a file picker. What am I going to save this thing as? I have to put up a dialog to the user and wait for them to answer. That's an asynchronous operation. Right here, co-await, picker, save, file, async. That's an asynchronous operation. I would have had to do a create task in PPL, which spins up a background thread, pass it a lambda or a .then function to run. Here I just say co-await. Kenny's going to go into co-await a lot more detail, so I'm not going to stress it here. And then once I have the file picked by the user, I open it. That's an asynchronous operation. Maybe it's a network file, and it's going to take a long time to open because I have to make a network round trip. Then I need a bitmap encoder. I want to save this as a JPEG. So I need a bitmap encoder, and I got to load all that infrastructure. And then I have to take the current visual for the photo, because maybe I edited it. I have to take the current visual, and I store that into a render target bitmap. And that takes a while, and that's async. Then basically, I tell the encoder to flush it to the file, and then I basically, in the last line, say, I'm really done making changes to this file, so if it's remote, now send all the changes to the remote system, so for efficiency. So I have, what, 6 co-awaits there? It just looks like procedural code to me. It looks all synchronous. I didn't block my UI thread or anything. We won't go into what co-await does. I won't. But it makes it really easy to deal with async methods. Co-await is actually part of, it just missed C++ 17. Microsoft and most compilers support it. It'll be officially part of C++ 20. But while the Windows runtime itself, or our headers, don't use co-await, we make it so easy that almost every client application ends up using co-await. And this is how hard it is. So with that, I will switch off to Kenny, and he will go into the details of what is DPP WinRT. I tried to give you just a high-level project system flavor. Now, what do I want to write? Here's Kenny.
Thanks, Brent. Very cool. So I want to switch gears a little bit and talk about some of the stuff that Brent spoke about, but looking behind the scenes, looking a little deeper to show you exactly what's going on and where you can get at this yourself. Let's say you don't like Visual Studio, you use some other tool chain, that's fine. You should be able to plug in directly yourself. So where I usually begin is with the dev command prompt. So I type x86 in the start menu, and up there you'll see the shortcut for the x64 native tools command prompt. From there, you really have Visual Studio 15.7 and the Windows SDK at your fingertips. All the tools that you need are right here. Specifically, I want to call out 2 tools. One is CL, that's our Visual C++ compiler, and you'll notice that that appears in the Visual Studio program files. You'll see host x64, x64 underneath. The idea there is we're cross-compiling, so there's a 64-bit host compiler that'll target ARM or x86 or 64 in this case. And then we have the C++ WinRT compiler. And there you see that ships in the Windows SDK, it's program files, and it resides in its own version folder. That version is the version of the Windows SDK. Now we don't actually ship a 64-bit version of CPP WinRT, that's an x86 binary. It just happens to show up in that path because that's where all of the 64-bit tools reside. But that binary is completely standalone. It doesn't even have a DLL for the CRT. It's all statically linked, which means you can now take that executable, CPP WinRT, copy this onto your build machine, run it from CMake, or whatever your tool of choice would be for building your applications. As an example, let's look at this little bit of code here. This is just a simple console app. I'm not really want to focusing on the code, but how the code is compiled. So I'm calling printf, which means I include sudo, and I'm calling some Windows API, Windows Foundation URI. So that comes from the Windows Foundation namespace. So back at the console, this is all we need. I'm calling CL. I'm saying limit the output, please. I want C++ exception handling. I want to target ISO C++ 17. And finally, I want to use Windows app.lib to resolve references. That's it. There's no Apex here. There's no certificates, nothing else. This is all you need to build your application today. As Brent mentioned, these are headers only. You simply include them in your application. Use CL or use Clang, and it works just fine. One final thing, he did allude to coroutines. So if you want to use coroutines in your application, you need to add /await for now until hopefully C++ 20 makes that available generally. Back in the application, there's one final question that we need to answer, and that's where does this header come from? So back at the console, we can also demystify that. So if you run set include, you'll notice all the includes paths by default for this dev command prompt. And right at the end there, you'll see under the Windows SDK program files, we also include a subfolder called CPP WinRT. And within there is that WinRT folder that Brent mentioned, where you'll find all of these headers. The neat thing is that you can run CPP WinRT yourself and generate those headers directly. So even if you don't have the Windows SDK installed, so let's imagine you copied CPP WinRT onto your old build server. You can then run CPP WinRT-in SDK. SDK is the option that it will basically find the latest Windows SDK that's installed on the machine and build the headers for that. You can also target a specific version of the SDK or just a custom set of WinMDs you might have copied onto that build server. Now, having said that, I want to focus purely on the code and show you some of the cool things you can do with C++ WinRT and focus on a set of practical tips that you can take away from this talk. And the first one is a set of things about async. So the first thing we want to do is make async synchronous. Now, one of the things that was very common in the Windows 8 timeframe is, well, we have all these great async APIs, but what if you don't actually care about UI, you're not building a UI application, and you get this silly error, cannot convert from. And so we have get retrieve feed async. We're building an application that downloads my RSS feed, but this thing won't compile, and it's because async is actually an IAsync operation of something, something, something. I just want the syndication feed out. How would I get that out? And as we alluded to before, we simply add the .get method. Much like std_futures.get, it'll block the calling thread until the result's available and make that available to the caller. If an exception occurs, it'll throw it at that point as well. The corollary is, what if you want to actually have async be cooperative? You actually are building a UI application, and then this is a bit problematic, because this get call here is going to block the UI, and you really don't want that to happen. So this is the case where coroutines come in really, really handy. So the solution there is twofold. First, we remove the trailing .get, and we simply insert or prepend the co-wait, forming a co-wait expression. Now, when you have a co-wait expression in a function, it automatically turns that function into a coroutine. Now, in order for it to be a coroutine and actually have it work, you need to choose a coroutine type. So this is the return type over here. Now, we provide a set of return types, or coroutine types, and they map to the WinRT async interfaces. And we will stitch this up for you so the compiler and the library, C++ WinRT, work together to create the coroutine on your behalf. The result is that you have a fully formed implementation of IAsync in action, in this case, that you can then return to a caller. The nice thing about this is that all of these types are WinRT types, which means they all provide an ABI. You can then return this to a C# application, and they can await the result as well. There's one gotcha that most people that are new to coroutines tend to run into. And I want to just highlight that here and make sure everyone's aware of this as we get started. There's exactly one character on the slide that's out of place. And that's this reference over here. When you're writing a coroutine, you must recognize that there may be suspension points. Suspension points are typically introduced by the co-wait expression, And that's a point in which the execution returns to the caller, and the coroutine may continue to execute asynchronously in effect. So let's imagine that constref is basically a pointer to the caller stack. And that stack may now disappear because executions return to the caller, and so that may not be stable. And so the solution there is simply to pass by value or capture by value. So if you're used to lambdas by now, you recognize that a lambda may be taken out of context, and you want to make sure that that executes reliably. Same story here, pass by value for coroutines. Just to highlight that one more time, on the one hand, we have a synchronous function. You want to use constref there. You know, if you're passing a std vector, you don't want to copy it. Same with WinRT types. You'd introduce a lot of interlocked overhead for the add, ref, and release behind the scenes. But in that case, for a synchronous call, you want constref. It's really efficient. You can call .get. For async, for coroutines, you want to make sure you capture by value, pass by value, and then you can use co-wait, and it works great. Those are your two scenarios. Sort of build that into your muscle memory. Now I want to look at some of the things we've done to dramatically improve performance by default. And the first one is optimizing string input. Strings are everywhere today, and they appear heavily in the Windows APIs. So let's imagine we have a simple API called toUpper. And you can imagine what that would do. It takes an H string as an input and returns the result. And we would naturally want to call this in a number of ways. So we might have an H string that we received from some other API, and we simply want to pass that in, and we should expect that to work. We might also have a std wide string, and like Brent mentioned, we want this to be able to work. And finally, a string literal should just work as well. The problem is this one won't compile. You see, a std wide string is allocated one way, and an H string is allocated another way, and they cannot be copied without an allocation in between. And therefore, we don't provide an implicit constructor to make that call work. So one option is to actually add an explicit constructor call there, and that'll certainly work. The problem is that both of these now are introducing hidden copies. When you have a literal, you don't know where that's allocated. You want to make sure we get a copy, so we introduce a copy. And both of those are not ideal, and certainly this is one of the things that we've seen very heavily in CX code, the number of copies that are created internally that are not helpful to your performance. So what we've done in the generated code, and I want to stress that this is in the generated headers, we use a set of param types. And these are specifically to optimize input binding. So all of the input types, where there's a significant benefit, we provide these special types that'll do the parameter binding for you and optimize these scenarios. So the param H string will actually bind to a std wide string. It knows the scope, it knows the lifetime, it understands how this should work, and it also works with a literal, and it avoids the copies for you. The thing to remember is that the language projection, the CPP WinRT compiler, will inject this where you need it. You don't have to ever add this type to your own implementation, to your own libraries. This is something that the projection does for you. So you can simply make the calls in the most natural way that you would expect. Building on that, we also optimize for collection input. So you can imagine an API that needs a collection of numbers. You can imagine what this guy would do, return the sum of these values. And we would want to call that in a pretty standard way. You might have a vector that you received from some other API. That's the WinRT I vector, or a std vector that you allocated locally. My favorite container type, it should just work. And finally, an initialize a list of values. Again, it should work. The trouble, again, is these two will not compile. iVector is just an interface. You need to provide some implementation somewhere. So who's going to do that for you? In CX, you'd have to explicitly say, I want a ref new platform, something, something, and it'll create one for you. But that's a lot of extra work, and we don't want to do that. So we have another param type, which is optimized for input binding for collections. And what this will do is it'll not only make this compile, but it'll also make it avoid the copies. So it again knows the scope of that, so it makes sure if you have a really, really large std vector, you can make this call, and the API, the callee, will get at that data without a copy, and make sure that it's also invalidated in case it incorrectly takes it out of scope. A slight twist on that is async. So we talked a lot about async already, and there's one gotcha here, and again, this is something we help you with so you can write the correct code by default. Let's imagine you have an API, some async. So we determined that this thing takes a long time to execute. You want to make it async, and so we have an async version of this. However, we have basically a constrained input scenario, so we want to make sure that all those bindings work, except that the std vector should not compile, because now, in this case, the std vector is clearly local, and you want to make sure that an async function doesn't reference local variables because the odds of this failing are extremely high. So we make sure that that is actually, it won't compile, but it will take an R value. So the L value version won't work, the R value will work. So it forces you either to copy the vector or to std move it and transfer ownership into the API. So again, very efficient, efficiency first, but as productive as we can possibly make it. Getting work on the thread pool. So now I want to focus more and more on actually implementation, on the implementation side of things. As we've seen, it's very easy to call APIs and make those calls, but how hard is it to actually provide these implementations? We've seen, like this example, how easy it is to create a coroutine and actually implement those async interfaces. But what if you actually want to get some work done? So I have this algorithm here. It wants to do some compute-bound operation. The trouble with this is that there's no suspension here whatsoever. And there's no point at which the caller is actually going to be, execution will return to the caller so the call is not blocked. And so what we need to do is introduce a suspension point. Even if you're not co-waiting some other operation, you need to make sure that we actually return to the caller and then immediately resume on the thread pool. And that's what co-wait resume background does for you. We have a set of helpers for coroutines specifically, and they work on the Windows NT thread pool. This is not the thread pool APIs in the Windows runtime. This is the very low-level Windows thread pool API, so it's incredibly efficient. But as you can see, it's very, very straightforward within a coroutine, within a function, to immediately switch to the thread pool to get actual work done. But one of the things that happens when you're working on a coroutine is that you actually want to make sure that you get, you may have to get onto the right context when you're done with your thread pool work. So let's imagine that a variant of that example. So we have this coroutine here. And we switch to the thread pool, but then we want to go and update that text block. It's a XAML control, it has thread affinity, and boom, it throws an h-result wrong thread exception. And the solution there is to capture the original context within which that coroutine was called. So for that, we have one option is the apartment context, and we can now capture the exact apartment context that that call comes from, and that happens to represent the thread for an SDA, for a UI application. So we capture the calling context. We can then switch to the thread pool, do some work on the background, and then switch back to the calling context. That ensures that we are once again back on that UI thread, and then this operation to interact with the XAML control will just succeed because now we're guaranteed to be back on that thread. So again, we switched two threads here, and incredibly straightforward and simple to write this code. However, with RS5, the new Windows SDK that we released this week, we can go even further and solve a little problem with a slide. So getting onto the right foreground thread is the question. In this example, how do we know that this is really the right thread for this text block? Let's imagine this coroutine was called from some other coroutine which had already switched to the background. There's no real guarantee that this is called in the right context. Now, you might write your application and you know that this is from some pointer pressed event and it'll just work. But if you don't, if you're writing a component and you really have no idea, we have a solution for that, and that's when we switch to the thread pool, after that we can switch to a specific dispatcher thread. So co-wait resume foreground, it'll use the run async method from the dispatcher in the background and stitch that together for your coroutine, making it very, very straightforward and simple, and in this case, very reliably get you back on the appropriate UI thread for a multi-view application. So that's a lot about coroutines. Let's talk a little bit more about specifically implementing interfaces. Because there we're implementing interfaces, but we're doing a lot of the hard work for you. In this case, we might have some arbitrary interface. So here we have iStringable. Now iStringable comes from the Windows Foundation namespace. So I say using namespace, and then I can simply call the toString method, which returns an H string, and I can use that. But how hard would it be to actually implement iStringable? Traditionally, this meant, okay, now I'm going to switch back out of the projection and use WRL or ATL or whatever you've used in the past for COM. And so let's have a look at what that looks like. So here's struct my type. I'm implementing something. Over here, I would declare the interfaces that I would like to implement. And then within the body, I can simply provide the implementation. Now, so far, this might look somewhat the same as what you'd have in ATL or WRL or some other implementation. But let's look at what that looks like here. In this case, I can simply declare I want to implement iStringable. That's a variadic parameter pack. And then I simply provide the implementation. And note that it has the exact same signature as the one that I called. So the caller will simply call toString expecting an hstring result. And in this case, I'm implementing it in exactly the same way. There's no virtual function. There's no hresult. The hstring isn't a handle, and it isn't an out parameter. It's simply the same signature as you would call. So this makes it very intuitive and natural to implement this correctly. If you want to go and create one of these, we need to call the make function template, and that bridges the gap between the implementation and the projection. So make will construct the implementation type on the heap, and then return the projected type. And we have a set of other, running out of time, so I'll make this brief, but we have a set of implementation helpers, make self, get self, and many others that'll help you to bridge that gap for more interesting scenarios. And it's all documented online now as well. And so here's another example. I want to add another interface, iClosable. I simply add the interface, provide the implementation, and it simply works. That's all there is to it. Behind the scenes, we do a lot of work to implement weak references. It's agile by default, marshallable, and so on. A more interesting scenario is creating collections. So in this example, you see I want to implement the iVector interface, which requires iIterable. And again, you can simply implement those methods. There's no hresults, no outparams. It's all standard C++. It's very convenient, but wow, that's quite a lot of work. You know, if you just have a std vector, you want to make some API call, that's a lot of overhead. Now, you've seen we use the parameter bindings, and we make this work for you. But if you're inside of an implementation, and you don't have the inclination to implement all these yourself, because notice you have to implement iVector view, you need to implement iIterator, and so on. We make it very simple to get that done for you. We have a set of helper functions, and here's an example of a single-threaded vector. So here, this simply creates a general-purpose implementation, and it returns an iVector interface implementation. And you can see the projected type there, and we can simply use that. We can append members. We can iterate over them. This is just a WinRT type, and you get to use it as you would any other type that you may have received from some API. If you need an iVector view, you can simply call the getView method, and it'll give it to you. So a very simple way of getting that done for most scenarios where you need to pass some data into an application or get some data out of an API to an application. Here's another example that really helps reinforce the value here. You may want to avoid the overhead of implementing or populating that interface across the API, and so you can start off with a std vector, do all your work up front, and then simply move the contents of that into the implementation, and that'll certainly work as you would expect. So we provide single-threaded vector. There's an associative container version, and there's observable versions as well. All of those are called single-threaded in the sense that they don't provide any concurrency. They're not thread safe. So these are really great if you're just passing data one way or the other across the API, and they get the job done for most scenarios. But this has nothing to do with apartments. These are all agile, but they're simply single-threaded. Again, in the RS5 Windows SDK that was released today, we also provide a collection of collection-based classes that you can do far more powerful things. If you need to add concurrency or type transformations, we do that as well. It's very, very straightforward. And as we wrap up, I want to talk about creating delegates and events. So creating a delegate in Windows Runtime is just an interface as well, but obviously a delegate maps to something more along the lines of a std function. It's a callable or invocable type. And so we make it very straightforward to actually implement those without having to go and implement an interface. So we might initially construct an empty one, and we can either initialize or assign a value to it using either a lambda, as in this example, or a free function or a member function. You can then check for validity, and you can invoke the delegate as you would expect any callable object. So very straightforward, certainly a lot more straightforward than C++ CX today, just in terms of the amount of code you need to write to get this done. And so the main scenario that we want to use delegates for in the Windows runtime is for events. And let me quickly show you how that works. So we might have an implementation, and I'm going to pick on the single-threaded observable vector function, which returns that iObservable vector implementation. It happens to have an event called vector changed. Now that vector changed event actually accepts a vector changed event handler. That's the delegate type, and it's a generic type. And so traditionally with C++ CX, you'd have to write ref new vector change, vector changed event handler of integer in this case, and then provide the lambda. We bind that up for you, so all you need to do is add the lambda, and we will infer the type and construct it behind the scenes for you very efficiently. then when you call the append method, for example, we will invoke that handler. One twist on that is if you actually want to deal with revoking the handler. So a simple example is simply to retrieve the result of the vector changed overload and capture that as a 64-bit token. We can then invoke the handler by calling append. That would invoke the handlers that are registered. We can then manually revoke the handler. It takes that 64-bit token, passes it back into the API, the event source, and then it removes it from the internal array that API may have implemented. Finally, the handler is no longer called because we've revoked that handler. So this is the most efficient, most straightforward way of dealing with events. But we have one final tip here for you regarding events, which is to use the auto-revoke keyword. The idea here is that this tells the projection to create an auto-revoker. The revoker itself, the object that is returned, is no longer simply that 64-bit value, but is instead an object that holds a weak reference to the event source. So the iObservable vector is held with a weak reference so that if the vector itself goes out of scope, the handler will automatically deal with that. So for example, when you want to revoke this manually, you can call a revoke method. And that'll attempt to resolve the weak reference to the collection. And if it still exists, if somebody else has a strong reference to that object, it'll be able to revoke it for you. Naturally, in its destructor, it'll also revoke that from you if you want to just store that in your class member and simply have that destroyed automatically. In either case, it's conscious that it's holding a weak reference, so that's very handy if you're dealing with reference cycles and you need to solve that problem within your application. And this is a very convenient solution for more complex scenarios. 2 more points. Implementing your own events. So let's say you want to actually implement that iObservable vector interface that we mentioned. You don't want to use one of the built-in functions. How do you actually implement the vector changed events? So first up, you can use the event class template. You provide the delegate type as its type argument. And then you can simply call the add and remove methods to add the handler to the array and remove that handler from the array. This does all the work behind the scenes for you. It's concurrency safe. It's thread safe. It'll make sure that it works reliably for you, and it's very efficient. Now, you don't have to implement the overload for the auto-revoker. That's taken care of for you by the projection. So this makes it simple. Now, the reason this isn't simply baked in is like you can imagine an implementation with 100 events. You may not want to use this implementation. You might want to use some kind of sparse event implementation. So you're certainly free to implement that yourself simply by implementing those overloads in whatever way makes sense for your application. Final tip. So with C++ CX, one of the things that developers did a lot, which they supposedly weren't going to do, was use C++ CX throughout their application. You were supposed to use it on the boundaries, and it was just too convenient to use it everywhere else. And so a lot of developers used events specifically throughout their application internally just for communication. And so to make that scenario very straightforward in terms of porting your code, we provide a delegate, a variadic delegate, which will work with any non-WinRT types as well. So you can use a std string, whatever else you like, and it works with the same event class template, and you can add and remove handlers and invoke events just as you would with CX, now with standard C++. But keep in mind that this doesn't provide an ABI. This is only for internals. This is just a helper to make your lives easier as you build or as you port your applications from CX. But it is very, very handy and useful. And with that, I'll call Brent to come up, and he'll close us off.
Thanks, Kenny. All right. So you've seen how to use Visual Studio in C++ WinRT. I should add that we internally are using it heavily. You remember the WRL code that I showed you, the page that's one line? Most of our Windows Runtime APIs are written that way today. Everybody that possibly can make the business case for it are rewriting in this. Our Surface device drivers are using this. We have in RS5, 33 DLLs are now using CPP WinRT. As fast as people are moving, they're moving to this. We find out with the WRL, there's like 100-to-1 line of code reduction. We found bugs because it's more understandable. It's more performant in many cases. We really want you to use it. We really want your feedback. So if you go to Visual Studio and you click on the report a problem, if you have a problem, we'll get the notification. If you have a feature request, please let us know. You can also go to Stack Overflow and ask questions like how to. It's not a bug or a suggestion maybe, but I want to know how I should do that. We look at a request tag that way as well. There are more resources here. Visual Studio and the SDK I've talked about, the extension I've talked about. The photo editor app, it does nearly all the stuff we've talked about today. And it's been reviewed over and over by our team as a guide for best practices. That URL is not live last I checked this morning. It will be in the next couple of days. It should take you to a landing page until the editor's alive. But we're going to put the whole source code to that editor app up on GitHub. Documentation has all been updated for us. Basically, you can go online, and if you go to MSDN or docs.microsoft.com now, you can get snippets shown to you in the CPP WinRT dialect, that projection. And with that, I'd like to close out. Thank you for coming. Please use CPP WinRT. We've spent the last 2.5 years working on it. We really want you to use it, and please say good things if you feel that they're true. And if they're not, throw the tomatoes and we'll dodge them and fix the reason you're throwing. Take care. Thank you.
Thanks very much.